Hi-ho everyone, Kermit the Frog here, and today we're talking about something very near and dear to my heart, the frog neuromuscular junction, or NMJ. That's right, this little spot is where nerves and muscles communicate to help us frogs leap, hop, and rabbit our way through life. Today I'm also thrilled to talk about the fascinating effects of verapamil, curare, and succinylcholine. First, let me introduce my amazing team, Ivana Castro, Emily Pearson, and Chrissy Patel. Together we hopped into the world of the frog neuromuscular junction. Let's dive into the heart of their project. We study nerve and muscle physiology using the frog-sciatic nerve and gastrocnemius muscle, along with the ever-important neuromuscular junction. In our experiment, we examined and compared the effects of verapamil, curare, and succinylcholine on the frog NMJ. Each of these substances does something unique to the communication between nerves and muscles, and we were curious to see how they would impact the NMJ. We also explored the threshold and recruitment of A-alpha motor neurons and water units, because understanding how nerves get activated is key to understanding how muscles move. And of course, we wanted to measure how these factors affect conduction velocity and synaptic delay, which tells us how fast and efficiently the signals travel between nerves and muscles. Let's talk about the neuromuscular junction. So imagine, if you will, an action potential, a little electrical signal zooming down an alpha motor neuron. Zunt! It travels all the way to the presynaptic terminal. Exciting stuff, right? Now when it gets there, it activates these tiny voltage-gating calcium channels. Boop! Letting calcium ions split in. Think of calcium as the superstar of the show, because it helps these vesicles filled with acetylcholine come to the edge of the neuron and go, ta-da! Releasing acetylcholine into the synaptic cleft. The acetylcholine then swims across the synaptic cleft, like a frog leaping across a pond, and binds to nicotinic acetylcholine receptors of the muscle end plate. This binding lets sodium ions rush in, creating a grade A depolarization called the end plate potential, or EPP. That's a big name for a exciting little spark. Now, if the EPP is big enough, like when all frogs jump at the same time, voltage-gated sodium channels in the muscle get activated, and we get a muscle action potential. Zap! The action potential stretches the muscle, making it contract. Ribbit-rific, isn't it? And that's how we turn the electrical signals into muscle movement. Science is magical. Alrighty then, now that we've covered how signals travel down the neuron, let's dive into the world of CAPS and MAPS. No, not maps for directions, but signals that help us understand nerves and muscles. So CAPS, or compound action potentials, are recorded monophasically, meaning the signal creates this single-phase wave, like a little hop. Meanwhile, MAPS, or muscle action potentials, are recorded biphasically, so the signal goes up and down, kind of like a frog jumping into a pond and leaping back out. Now about their amplitudes, that's just the height of the wave from the baseline to the peak. CAPS are smaller, like a tiny frog hop, measuring 3.74 millivolts in our example. The MAPS are the big jumpers, coming in at 17.55 millivolts. And then there's latency, which is how fast these signals travel. CAPS measure from the start of the stimulus artifact to the wave's peak, which took 1 millisecond. Super quick. MAPS measured to the start of the MAP wave, taking 2.94 milliseconds. A little bit slower because, well, muscles like to take their time. So in summary, CAPS are like the nerves whispering, and MAPS are the muscle shouting, "Let's move!" Ribbit-rific, right? Alright folks, let's hop into the mechanisms and applications of the treatments we've been exploring. First off, verapamil. This is an L-type calcium channel blocker. That's a fancy way of saying it helps stop calcium from entering cells, which is really important in controlling things like epilepsy, high blood pressure, and even certain heart arrhythmias. So verapamil helps keep things in sync, kind of like how a frog stays in rhythm with its jumps. Curare. This is a nicotinic acetylcholine receptor antagonist. What does that mean? It blocks acetylcholine from doing its job, which leads to muscle relaxation. It's mostly used during anesthesia to keep muscles relaxed so doctors can do their work without the muscles jumping all over the place. And then there's succinylcholine, an acetylcholine receptor antagonist. It's like a frog jumping onto a lily pad over and over. It overstimulates the muscles, causing them to relax temporarily. This is a commonly used in emergency medicine and clinical anesthesia to help with things like intubation and other procedures. So whether it's calcium channels, acetylcholine receptors, or muscle relaxation, these treatments have a horrific impact on wholly managed medical conditions and surgeries. Verapamil acts on all-type calcium channels, which is expected to have no impact on NMJ function in this experiment, as the NMJ is composed of PQ-type calcium channels. Curare binds to nicotinic muscle acetylcholine receptors to inhibit acetylcholine from binding. This reduces the sodium influx and the end plate potential will diminish due to less depolarization at the end plate. Succinylcholine mimics acetylcholine and binds to nicotinic muscle acetylcholine receptors, resulting in prolonged depolarization. The voltage-gated sodium channels get stuck in this inactive state. The methods mainly matched what was in the lab manual for the NMJ experiment. We looked at the effects of each drug on NMJ function, threshold, and synaptic delay. We tested the drugs in order of least toxic to most toxic, with verapamil, curare, and then succinylcholine last. For verapamil threshold and recruitment, no effect was expected to be seen. The threshold remained the same as well as the cap amplitude. The map amplitude decreased slightly from the control, but this could be due to cross-reactivity with the PQ calcium channels in the NMJ. For threshold and recruitment for curare, the threshold remained the same, because motor neuron properties were unaffected. However, the map amplitude was expected to decrease due to curare decreasing the end plate potential, leading to less depolarization and less motor units being recruited. Some motor units are still able to reach threshold despite curare blocking some of the nicotinic muscle acetylcholine receptors. The cap amplitude remained the same as the nerve was unaffected. For threshold and recruitment for succinylcholine, the threshold remained the same as again motor neuron properties were unaffected. The decrease in map amplitude was expected due to succinylcholine causing prolonged depolarization, keeping the sodium channels inactivated. To measure synaptic delay, first, the time between the peaks of the two caps when the electrode was moved an extra 10 millimeters was measured, which in this case was 0.29 milliseconds. The conduction velocity was then calculated by dividing the distance traveled, which was 10 millimeters, by the time it takes to travel this distance, which was 0.29 milliseconds, and this equals 34.40 millimeters per millisecond. The conduction time was measured by taking the distance between the negative stimulating electrode and the negative muscle recording electrode, which was 40 millimeters, and dividing that by the conduction velocity, which is 34.4 millimeters per millisecond, and this equaled 1.159 milliseconds. The map latency was then measured by measuring the time between the onset of the stimulus to the onset of the map, which was 2.96 milliseconds. The synaptic delay was then calculated by subtracting the map latency minus the conduction time, which was equal to 1.8 milliseconds. The synaptic delay for verapamil was first calculated, where the control delay was 1.8 milliseconds, and the delay after treating the muscle with the drug was 1.82 milliseconds, meaning the synaptic delay did not change significantly, which matches the expected results as the synaptic delay was not expected to change. The cap conduction velocity and time stays the same due to the properties of the A-alpha motor neurons, like size and myelination, and the nerve was also not treated with verapamil. This is true for all pre-treatments that were used on the muscle. The map latency should also not change since verapamil only acts on LTCCs, which are not present at the NMJ. The main calcium channels that are PQ calcium channels in the presynaptic terminal. Because verapamil does not act on these PQ calcium channels, the map latency and hence the calculated synaptic delay should not change. The synaptic delay for Chiari was then calculated, with the control delay being 2.29 milliseconds, and the delay after treating the muscle with the drug was 5.07 milliseconds, meaning the synaptic delay increased significantly, which again matches the expected results. The conduction time remained the same while the map latency increased because acetylcholine cannot readily bind to the nicotinic acetylcholine receptors that cause the polarization due to Chiari blocking these receptors. This led to a longer delay in initiating the end plate potential. There is also the added time it takes for the nicotinic acetylcholine receptors to be activated, and then a sufficient sodium influx still needs to occur so that an end plate potential above threshold is generated. Because of Chiari binding and blocking these receptors, it takes longer for the M-plate potential to accumulate and to reach threshold, thus increasing the map latency and synaptic delay. Lastly, the synaptic delay for succinylcholine was calculated, with the control delay being 1.94 milliseconds and the delay after treating the muscle with the drug being 1.93 milliseconds, meaning the synaptic delay did not change, which does not match the expected results as the synaptic delay should have increased. Both the conduction time and map latency did not change. The map latency was expected to change as the prolonged depolarization of motor units inhibits the action potential from being initiated. Additionally, acetylcholine cannot readily bind to the nicotinic acetylcholine receptors due to succinylcholine, which has a longer enzymatic breakdown period. The synaptic delay likely did not increase due to succinylcholine not reaching all of the synapses at the NMJ when the drug was administered on the muscle. In conclusion, extracellular recordings from a frog sciatic nerve and gastrocnemius muscle were used to examine the effects of rapamycin, curare, and succinylcholine on things like overall NMJ function, Dresdelden recruitment, and synaptic delay. Thank you for watching.